extremely simple because on that particular example, you already see a lot of the difficulties, a lot of the techniques that have to be applied. And it's sort of a realistic example to some things. And it's just one-dimensional. So we can just speak about the Hessian being a number instead of having to deal with the eigenspectrum of the Hessian and just add one extra layer of complexity. And in fact, if you look, what the problem is something like where you have a bunch of examples, they're just numbers in Rn, in R, real numbers. And what? You have one parameter, it's also in R. And you want to optimize the average of xi minus w squared. And the solution that is well known is just getting w to be equal to the mean of the xi. So the problem is not that interesting. But it's a good problem to start the situation. And also you'll see that already is not that easy. Actually, I've seen that yesterday. So what's the... no, I need to do send to screen. Yes. So this is my parabola. And for simplicity, I'm just going to assume that the mean is 0, because that doesn't change anything. So my function is 1/2 of hw. So h is a capital, but it's a number, just w squared, with optimum in 0. And my gradient has the form derivative of the function plus some noise that comes from the xi's I'm choosing. In fact, the xi's are precisely the xi, but that's in that case. So I can write it with hw plus the noise. I assume the expectation of the noise is 0, and the variance of the noise is g. So if we didn't have noise, there is all this well-known mathematics about gradient. I can write the update this way and just replace the gradient by hw. And I said that wt becomes 1 minus eta h transpose w0, not transpose, to the power t w0. So it's a geometrical series. If the gain eta is small enough, so it's less than 2 over h, the absolute value of this is less than 1, and you have convergence that's exponentially fast. And this is why in the set of asymptotic rates that had been before, for the gradient, you reach a certain error, a certain accuracy in optimization at a speed that's in a time that's proportional to log 1 over the accuracy. So let's add the noise. So I write my stochastic gradient algorithm here. And I have the same thing, but I have my noise term. And the noise term, I noise a lot. So I'm going to try to estimate wt squared. So I square this formula, and I develop my noise and my noise. I take the expectation given everything I know up to time t. So now the expectation of the noise is 0, it goes away. And this one becomes a g, the variance. And I take the expectation over all possible times. So I can have wt minus 1 here and here, so they go together. I have another one here, so I get this product, expectation of w squared t minus 1 plus eta squared gt to the minus 2 alpha. Well, my gain was the form n t to the minus alpha. So what I have here is a recursion that tells me how the expectation of the error I'm making in the quadratic sense is decreasing or not decreasing. And all the problem now is to analyze this recursion. So that's the recursion. I call now the thing ut before simplicity equal this coefficient, ut minus 1 plus. And what I can do is I can apply it repetitively. So I can replace ut plus 1 by the expression and do it again, until I reach a certain starting point that I call us. And I find two terms. The first one is the starting point times the product of all these multiplicative terms. And the second one is the compounded effect of the noise factor that comes from here. Now, the first thing we can notice is that when alpha is less than 0, meaning that the gain increases, everything diverges because my multiplicative factors, they get greater and greater. So when I multiply numbers that are bigger and bigger together, it's not going to be pretty. When alpha equals 0, meaning that my gain is not decreasing, so this is a constant. And if this constant actually in absolute value is greater than 1, the thing diverges. If it's less than 1, well, this first term is going to go to 0. And the second term actually is not. And that's, I'll leave that as an exercise. It's not too mean. So what I'm going to do for the other case is first I'm going to choose my S wisely. I didn't say U0, I said US. Yes?
I'm just curious, but the matrix H, is it a matrix of functionals or constants?
It's a real number. I'm in one dimension. My function is, this is my function, 1/2 of HW squared. This is what I'm trying to minimize.
So you're saying that the derivative is going to be a linear combination of W or of W?
The derivative, the thing I'm going to use for my updates is the derivative of f, which I can write as HW, plus some noise. Now, this is not such a silly thing, because if you think about a real problem, locally, close to the optimum, you can make a second-order Taylor expansion, and it's sort of quadratic, just in multiple dimensions. So you have to deal with the eigenvectors and eigenvalues of the Hessian matrix, and that makes things more complicated. But this complication is not something specific to stochastic gradient. When I'm doing it that way in one dimension, I'm seeing the complications that are specific to stochastic gradient. And then at some point later, I'm going to put things together, and I'll just give you a sketch of how it's done. So I take this problem, this stochastic algorithm, I obtain this recursion. So I was at the point where I speak about the S. I didn't say U0, because if you take alpha positive, meaning that the learning rates are decreasing, you see that these terms and these terms, they're decreasing as well. So there's going to be a moment where you're guaranteed that the multiplicative terms are not negative. So if they're negative, basically what's happening is that you're going first to go all over the place, because you're going to have an amplification of the starting position. So it's going to move quite widely. And then at some point, they're going to become smaller. These multiplicative terms are going to become smaller than 1, and maybe you're going to converge. So this is something you would like to avoid. So when I'm in a situation where all these product terms, these terms in the products are positive, these two things are positive, and I just need to see how these two terms converge separately. So I start with the green term. So remember, you see this product here. And the good way to do it is what I call AST, is going to be the sum between S plus 1 and t of the log of the product. And so basically, that's the log of my green term that I'm discussing here. And I'm first looking at the case where alpha is between 1/2 and 1. So I have my sum of the log. And the log 1 minus something that's small, it can be approximated by just the minus thing. And you have second-order terms. This one is a second-order terms, and you have other second-order terms that come from the approximation of log 1 minus x by x. So now I have this series, and I approximate it by an integral. So instead of having sum from s plus 1 to t, I'm going to say integral from s to t or x minus alpha. When I'm doing this, I have an error that's bounded. It goes into this O of 1 now. And also, because alpha is greater than 1/2, the j minus 2 alpha in this residual term is something that decreases faster than j minus 1. And because it's in a sum, it's a convergent series. So it also goes into the O of 1 here. A big O of 1, meaning that this is constant plus something that goes to 0. And then I can take my integral, and I say it's going to be kappa t at the 1 minus alpha, where kappa is just the constant term that you have there. Then my green term that I can write as US exponential AST, it's equivalent to exponential minus kappa t1 minus alpha. It goes to 0. Basically, the green term converges exponentially to 0 when alpha is between 1/2 and 1. OK. Good. That's just the beginning. So the case where alpha is between 0 and 1/2 is a bit more complicated because you cannot say anymore that this is a convergent sum, and you have to deal with the second order term and see that they're actually negligible compared to the first one. And it's not that interesting because you don't go any faster or anything like that. So actually, you go slower. Now, let's look at other values of alpha. There is alpha equal 1. So I write exactly the same thing, but this time the integral gives me a log. I cannot use the 1 minus alpha. So when I do this, I get that I converge like t to the minus 2 eta h. So this time my green term is, here I had the green term that was exponentially to 0, not very fast because t to the 1 minus alpha, that's not that fast. But here is something that's slower. It's polynomial to 0, and the degree depends on the eta that's in the learning rate. OK. And you have the case alpha greater than 1. Oh, good. But then when I write my sum here, I see that if alpha is greater than 1, this sum converges when t grows. And this sum converges. So everything tends to some k that's greater than minus infinity. Because that means that the green term, US exponential AST, converges to something that's greater than 0. That means that my process doesn't converge. And this is why I can see that I cannot decrease the learning rates too fast. Otherwise, I'm just going to stop in my optimization away from the optimum. Now, the green term is the easy one. If you remember the red term, it's this nasty things here. And what you have in the red term is that if you compare the red and the green, you have this product, but instead it's the product from I to t instead of the fixed starting point to t. So I need to estimate that properly. So let's take the red term with alpha equal 1. And instead of AST, I have AIT, same decomposition, but this time the sum starts with I plus 1. I approximate by an integral, and I can write minus 2 eta h log t minus log I plus O of 1. Then I can put that back into the red term. So I have sum from I equal s plus 1 to t eta squared g I minus 2 exponential AIT. And by removing the constant and everything, this is equivalent to t to the minus eta h, that comes from this log term, yeah. Sum of I equal s plus 1 to t of I minus 2, I to eta h, that comes from this log I here. And this is another sum that I can approximate with an integral. So if I take the integral of 2 eta h minus 2, I get a 2 eta h minus 1 between two terms. And if I simplify, I remove the constant and everything because I'm working in equivalences, I simplify, I get t minus 1. So all this to say that the red term converges like t minus 1. So let's see if we can do that for the other interesting case, which is alpha between 1/2 and 1. So I write exactly the same thing with my alphas. And so for the blue part, that's OK. I have an estimate of AIT that's simple. I have the integral. I can write x 1 minus alpha over 1 over alpha. There is the kappa term that's the same one as last time, and a difference of two exponents of t and I. And I put that back in the red term, and I find this thing with this nasty thing here. And the problem is that we would like to approximate this like with an integral, but the primitive of x minus 2 alpha exponential kappa I to the x, actually x to the 1 minus alpha, sorry, that's not very obvious. So, well, we cheat. We're going to add terms that do not affect the asymptotic rate. So I start from this expression, and I'm first going to take my I to the minus 2 alpha and add a constant in front, kappa to the 1 minus alpha. And that doesn't change the equivalence, it's just a constant. Then I'm going to add another term, minus 1 plus alpha I to the minus alpha minus 1. Now, because alpha is less than 1, this other term is smaller because minus alpha minus 1 is less than minus 2 alpha. So because it's smaller, I'm just adding a lower order term. It doesn't change the asymptotic rate. But the neat thing now is that this is the non-derivative. This is the derivative of x to the minus alpha exponential kappa x 1 minus alpha. And this is where I choked yesterday, actually. So I can approximate this by integral, take this between t and s, and I see that this is equivalent to t to the minus alpha. So after this derivation, I have my summary. When alpha is less than 0 or alpha greater than 1, the thing doesn't converge to 0 or diverges completely. When alpha is between 1/2 and 1, and also between 0 and 1/2, but I didn't prove that directly, it's just like t to the minus alpha. When alpha equal 1 is t to the minimum of 1 and 2 eta h, because the red term goes like t minus 1, and the grid term like t to the minus 2 eta h. So I have these two terms to balance. And if you do simple stochastic gradient descent, you typically have these two terms to balance. The term that tells how the initial conditions are being washed away, and the term that characterizes how the noise enters the equation. And you have to balance them right. If you go to more sophisticated variants of stochastic gradient that I'm going to discuss soon, it's actually worse. You have 4 terms to balance and things like that. So the conclusion is that the best convergence speed I can achieve with a stochastic gradient is order t minus 1, and I have to have the right gains. Alternatively, I can decrease a little bit slower, like minus 0.9. And I don't have the same problem, but in fact, it's just asymptotically, it's just as good. But in the transient, you're just going to lose the same thing. And I made the point that this is a convergence speed that's quite bad for an optimization algorithm, but in terms of statistics, it makes sense. And this is what takes me to the kind of rates I was using in the discussion of the asymptotic rate of stochastic gradient. So I'm sorry to impose on you this bunch of equations, but I think it's useful to see this kind of derivation because, first of all, it's quite accurate. This is not a bound, this is a rate. And I could work on the constants as well. If you're more refined in the way you do things, you can compute the constants and know things pretty well. So it's quite different from the typical things you see where you actually bound convergence rates from above or from below. Here you get the real thing right away. And I'm going to show an application of this. I have half an hour, so I'm going to jump elsewhere in my set of slides. Nope. OK. My problem now is that when I have a really large data set, you've seen that the loading time is longer than the training time. So I wouldn't want to load the things. I would just want to take them directly and learn and forget about them. That means that I want to learn in one go over my examples. So can we actually do that? Can we come close to that? So I'm going to consider 2 possible ways of doing it. Suppose I have a set of examples, Z1, Zt. What I can do is run the stochastic algorithm from 1 to t, and I reach a certain point that I call Wt. What I can do too is take sets of examples are increasing from Z1 to Z3, then Z1 to Z4. So I'm adding them one by one. And for each set of examples, I compute the batch optimum, the optimum of my training function. And I get a sequence of solution W1 star, W2 star, W3 star, to WT star. Now, the thing I would like to have is the best generalization error that I call simply W star, the best one in the family. Now, if I continue my set of examples indefinitely and my algorithm is half good, meaning that the loss function is not crazy or anything, it's going to go there. When I speak about the convergence of stochastic gradient, I'm saying that if I'm drawing examples from a training set, I converge to the training optimum. I'm also saying that if I'm drawing examples from nature, so a different one, a new one each time, I'm converging to the generalization optimum, the test set error, basically, the best test set error. So this one would go there. So what can we say about these convergence speeds? If they're about the same, that means that my point WT is just as good as WT star. So I'm first going to study the W star. What's happening to the training optimum when I'm adding one example? So suppose that W star n is argmin of W of En of W. That's my cost. W star n plus 1 is argmin W of En plus 1 W. That I can write as En W plus 1 over n, the loss of the last one. So actually, they have a correction to do somewhere. OK, fine. This is actually n plus 1 over, this expression is n plus 1 over n greater than En plus 1. That's fine. So the basic idea is that I'm making a small perturbation of my error. So I'm moving my cost function by a little bit. And therefore, the W star is going to move by a little bit. And the question is how much? Well, you can do it. You do a first-order calculation. It's just a relatively simple calculation with the error function. You add the little things. You do, actually, second-order calculation you add. And you find this expression here. You find that W star n plus 1 is W star n minus 1 over n. So Hn plus 1 minus 1, this time is a Hessian, multidimensional. And that's the empirical Hessian measured on all the examples I've seen so far. The derivative of the loss with respect to the new example plus higher-order terms. And if you compare with the second-order stochastic gradient descent, well, this is almost the same thing. While we don't have the second-order term, here you have supposedly the real Hessian instead of an empirical one. But these two expressions look about the same. And you might wonder whether they converge with the same speed. So you've seen the calculus I just did before. Now we have to do it in multiple dimensions with things that are not necessarily quadratic. So you have residual terms all over the place, with additional residual terms that are in the thing. So I'm not going to do it or impose that on you on detail. I'm just going to show the basic steps. So there's something I call the scale stochastic gradient descent, which is the same as the gradient descent. I take a learning rate in 1 over t, and I use a matrix BT here. And this matrix, I suppose, is definite positive, and it's told that BH is greater than or BH minus RDTT over 2 is definite positive as well, which is the way to say that I'm in the fast regime of my convergence, where H is the Hessian in the optimum. So the first thing is that to make sure that all my little terms, residual terms converge, I need to prove that this converge. I didn't show yet how to do it. I'm going to show that next time. And then I can define an error term. And my error term is going to be a matrix. UT is not going to be a scalar. It's going to be H WT minus W star times WT minus W star transpose. And I use this matrix because I can observe that the expectation of WT minus the expectation of W star is the trace of UT plus residual terms. Because if I'm at the optimum, there is no derivative. The average derivative is 0. And I'm left with the second order term, and this is what this is meant to approximate. I go on. I establish a recursion. It's about the same thing. there is a matrix G that comes out. That's actually the Fisher information matrix, which is basically the covariance of the gradient at the optimum. So the G here plays the same role as the variance of the gradient, except this is the covariance at the optimum. Then I have my thing here is that I have a recursion that has this form. And I'm going to work first on one-dimensional sequence where UT is a real, satisfying this. And you can show that when alpha is greater than 1 here, UT is beta over alpha minus 1 over t plus higher order terms. And when it's less than 1, it's actually slow. And that's the same kind of recursion as the one we have. It's just a lot more complicated because of the residual terms. Then we can bracket the trace of what? Of UT plus 1, the parentheses extra, using two such sequences. And you get the results that, and this is both an upper bound and a lower bound, and they're very similar, that the expectation of the excess error is between some constants 1 over t plus residual terms and some constants 1 over t plus residual terms. And there are two interesting cases. If b equal h minus 1, so basically you do a Newton algorithm, or b basically the bt, the scaling term, tends to h minus 1, which is what you have for the w star, these two constants are the same. That means that in that case, you know precisely the convergence rate and the constant. And the constant is defined. So what does it mean? Let's go back to my problem here. It means this. It means that n times the expectation of my error, the excess error for w star n, it's equal to t times the expectation for wt here. And they're equal to k over n with the same constant k, which is quite, I can only say that because I can make the calculation that accurately. And the same constant k means that my wn and the w star and my wn star and the w star, they're about at the same distance. They decrease the same way. That means that if I do one pass of second order stochastic gradient, asymptotically, I'm just as good as if I had the best training set error. And the first one says that about the excess error. I'm generalizing just as well. So I need to hammer that again. A single pass of second order stochastic gradient generalizes as well as the empirical optimum in the limit. So here are some experiments on synthetic data. So the blue one is the single pass of second order stochastic gradient. The red one is the empirical optimum. This is the test error. This is the number of examples. And this is a situation where doing a single pass of stochastic or the second order stochastic gradient, you actually go faster than using the Newton method you use it to compute the empirical optimum. So can we use that? Because that says, this is a theoretical result. It tells you that if you do second order stochastic gradient, and you do it right, and OK, you implement it right, and you have the gradients right, you just need to do one pass if your exams are properly shuffled. But there are some issues that are nasty. The second order SGD is costly because you need to multiply for every single example by this matrix h minus 1 that can be large. And you have to estimate the matrix to start. You have to estimate. So if D is 50,000, 50,000 times 50,000, it's not going to be good. It's not going to be something you want to invert. And you need to do it for every simple example, every 800,000 of them. Not good. But there are some solutions. There is one family of solutions is to use limited storage approximation of h minus 1. And you can do diagonal Gauss-Newton, which is what Becker and Lecan did in 1989. You can do other diagonal approximations. So that's Antoine Borde did that with SGD-QN, and they won this large-scale competition a little bit by chance because the algorithm was broken. Schrodolf has a nice, and Vichy actually, you have this nice online LBFGS that's a low-rank approximation. So you can do these things. And there is a method that's actually very surprising. And to be absolutely honest, when I write the derivations and I get the result, I still don't understand how I get there. I don't have the intuition. Instead of having 2 terms to balance, you have about 4, and you have to balance exactly right, and suddenly things happen. So you do SGD with gains that are slowly decreasing. Instead of t minus 1, you're going to do something like t to the minus 0.75. Or t to minus 2/3 is quite common as well. And at the meantime, you compute the average of all the weights you've seen from the beginning. So that's an iterative computation of the average, where I take a t over t plus minus 1, the previous one, plus 1 over t plus 1, the new one, and I keep averaging. First of all, that works only for convex loss functions. Because what it does is that you have this ball, and because you don't decrease the learning rates very quickly, your stochastic gradient flies on top of the optimum. And when it flies on top of the optimum, you average the cloud and hope that you'll be in the middle. Now, if your ball is twisted like this, you're going to fly a little bit like this on the side, and the average won't be right. This is why you still need to decrease the learning rate so that you go to a situation where the ball is roughly symmetrical. But when you do this, you can prove a result where this has the same asymptotic speed as the second order SGD, which means that this, in theory, if you get all the constants right, should go as fast, should achieve the same kind of excess error on the test set than computing the real optimum. Just doing one pass of this. Now the question is that this asymptotic regime is a bit tricky to reach, and so you actually need to do some work before you reach this. So that works when you have a large data set. So let's look at examples. So this alpha data set comes from the Pascal large-scale challenge. And you see in red the SGD. That's the number of epochs. And the expected risk, the SGD. The green one is the SGD quasi-Newton. It starts well, but then at some point. So basically, what it does, it finds quickly the diagonal coefficients that would be the right scaling. But it's limited to only diagonal. So it cannot finish the job and ends up pretty much where SGD is. And the average SGD just goes down and flattens. And what you see is that, well, pretty much reach the optimum after one epoch. Now, this, in terms of test error, is not any better than this. If you look, that's the expected risk. If you look at the test error, well, actually, there are some things happening there because the cost you optimize is not exactly the test error. So maybe you need to do 2. But that's good. Now, if you take a problem like the conditional random field, so this one has a lot of parameters and not so much training data. So it's a situation where it's more challenging to actually reach the asymptotic regime. So if you look at the test loss, the stochastic gradient, that's the thing that runs in 10 minutes instead of or 1 hour and something. Well, it looks slow now. The SGD-QN and the ASGD, they do quite well. And the SGD-QN is actually a little bit better on that one because the average SGD cannot reach the asymptotic regime on so few examples. So the training times were on the 500 seconds. That's not the same computer, sorry, for SGD. So that's close to 10 minutes. There are 150 seconds for SGD, 75 seconds for SGD-QN, where the standard optimizer used 72 minutes. So that's a fast CRF. And if you look, well, here you need something like 5 epochs to get some things correctly. So, well, these are also sparse problems. Actually, alpha wasn't sparse, but the CRF was certainly a very sparse problem. And you have to use the same kind of little tricks. First of all, that's the learning rate I used. This one was on -0 to -3/4. That was how we implemented the sparsity preserving implementation in the SGD. For the ASGD, actually there was a trick that comes from Wei Xu, who used to work in NEC. And now I think he's in Facebook and he disappeared. I know he has a draft somewhere of a paper that is submitted to GMLR, but I'm not sure he went through. I hope he will at some point. And he had this absolutely crazy trick. So you do the same thing for the gradient part as the SGD, but there is a way to write the average like this, Well, if you write it this way with this exact value of RT, the update on UT is going to be sparse as well. So you go full speed. And for SGDQN, the way we did it, that was with Antoine Board, there is a decoupled, it's the same thing as what I described for the SGD. We decouple the slow updates and the costly updates, the cheap updates and the costly updates, and we do the costly update less often but stronger, and we compensate. So, what time is it? Well, so I went way faster than expected, as usual. So learning in a single epoch. One epoch learning in practice. For a convex objective function with a sufficiently large data set, it's possible, it's doable. So sometimes I want to be provocative. I did, you don't need complicated hashes, you don't need to load things in memory. Just pull them from the disk and throw them away. Go once on the data, you're done. But there are other considerations. Like if you have a very large data set, it doesn't come like an IID sequence. Usually it comes from various sources, or maybe it comes in time. So you want to shuffle it. And shuffling a large data set can be hard. You know, if you have something that's hundreds of times faster, hundreds of times bigger than the memory of any single machine, shuffling it is a challenge. In fact, the simplest way to shuffle it is probably to draw a random number and do a list merge sorting between all these things, which is not that fastest on petty machine. And the other question is how large a data set we need to reach this kind of a regime? Well, see, for the alpha data set that worked quite well. For the CRF, we were not there yet. So I must reduce the claim. A couple epochs are enough. And that's probably the answer to Vichy's question this morning, that when do you need to stop? OK, do the algorithm well and do 5 epochs, and you're fine. That's all I have for now. Then what I have is another series of... so I guess it's time for questions. Yes?
So did you have an answer for what to do when shuffling is hard? I mean, is there an answer for that?
Is there an answer to that? No very good answer. The thing is that if you want to shuffle a data set, and that is distributed on plenty of machines, and it's much larger than anything on any of the machines, well, the best way I know is to use a sorting method. You draw a random number for each of your item, and you do a list merge. But the list merge between several machines is going to be hell. So what you can do is cheat a little bit, but then you lose the theoretical properties. So you say, well, I'm assuming that the data set on every machine are similar enough. I shuffle locally, and when I'm pulling examples, I'm pulling them from a random machine, and I go around. So that's a way to do it somehow. But you still need to, the bottleneck of these techniques is that you still need to pull every example into a single processor that's going to update the weights. Because it's an averaging, and I think Alex Mola tried things like this. What you can do is have several systems doing this on several machines, on several data sets, and at the end, you average the weights of all of them. But when you do this, you rely a lot of convexity. So, well, if you're non-convex, non-convex is important. I'm going to come back to that. Another question? Yes?
I have a question. You have this assumption that you said gamma t equal to n dot times t to the power of minus 1, right? Where does the assumption came from? When you do an analysis of your how fast you converge?
The analysis at the beginning, the one-dimensional analysis.
I guess it's slide number 28.
28. Yes, well, I had it here, the one I have here. This one?
No, go slide 28. You have this, so you added this stochastic noise.
Yes.
And you set gamma t equal to nu t to the power of minus alpha, right?
Yes.
So why exactly this formula? Why not exponential term? Why exactly? Even the decreasing will be according to...
OK, because experience has shown that t equal eta t minus 1. t to the minus 1 is not a bad choice, that you look at polynomial, that if it's exponentially decreasing, it's going to be super slow, because basically you can actually do the calculation. The second term is not going to decrease very nicely. You know that, and then you have an intuition too. You have the ball of the cost function, and you're flying on top of the optimum. You're moving randomly around on top of it. Like, it's not a Brownian motion because it's biased towards going to the bottom. So, and if you reduce the learning rate, you're going to fly lower and therefore be closer to the optimum. So you want to reduce the learning rate as fast as you can. But if you reduce them too fast, what's happening is that, well, if you reduce them, like, for instance, exponentially, the series of, suppose you're on a plane that's just like this. The optimum is very far away, so the gradient is constant. So the update you're going to do on total is going to be the sum of the learning rates, because the gradient is, let's say, is 1. If the sum is convergent, you're just going to stop. You're not going to go to the bottom. So you cannot, it's a bad idea to have a learning rate that decreases so fast that it's a convergent sum. So exponential is therefore to decrease too fast. So what's there next, t to the minus alpha, is something reasonable. And we know that more than t squared is already too fast. T greater than 1, alpha greater than 1 is already too fast. OK?
Can I add some intuition to that?
Sure.
So if it's, you know, you want it to be such that you never stop learning. And if the sum is finite, then essentially you can get stuck without getting to the final answer. So you want the sum to be infinite. And you want the sum of squares to be finite, because you want the...
Actually, this one is more...
Sorry?
This one is, you find it in the convergence proof in some cases, but you can navigate around that one,
yeah.
the sum finite. But one point that's related to what you say is that suppose you want to have a system that's online and keeps adapting all the time. What you want to do is to keep a learning rate that doesn't go to 0. Because it's OK to fly on top of the optimum if the optimum moves, because you keep the ability to track it. So there is a complete and separate domain of studies where you study the convergence with fixed small learning rates, and you study the tracking properties of stochastic gradient. And that's also something interesting. If you do something that varies in time and data comes in time, you can try to use this to track. But then you have to balance the goal of being close to the optimum and keeping the ability to track. It's not always easy. And averaging doesn't work. Yes?
What about cases where most of the time there's this kind of drift that you're talking about, but every now and then there's not a sharp change, still a continuous change, but a faster change. And then you may be able to model when those changes happen.
Well, people in adaptive signal processing did a lot of work on that, because this is basically how you code things. So suppose you send a signal along a wire, they're going to be perturbations. So what was constant at some point is going to drift a little bit, and you need to track this drift. But sometimes you change the signal. You go from a bit 1 to a bit 0, and there is a sharp movement, and you need to detect that on the other side. So what they typically do is they have a tracking that's a bit smooth, and when the tracking becomes off prediction, basically it doesn't predict the signal well anymore, you can deduce that there is a change. You know that there is a bit. You output the bit, and you reset your system to the new state, and you go on. That's a simple way. They have a lot more sophisticated ways to do all this adaptive error correcting or adaptive signal filtering. And there is really a lot of work on that. Most of the work on stochastic approximation was for that application. Yes, sure.
So when you're doing the diagonal approximation of stochastic gradient descent,
yes.
can you thought about approximation also all diagonal edges? Is it possible?
All the diagonal?
So your problem is you're trying to approximate Hessian in order to simply
Yes.
Find multiplication.
Yes.
Maybe you can solve the first task by calculating the Hessian, not exactly but approximately.
Well, you still have to store it. So there is this limited storage approximation of the Hessian. You can represent the Hessian like a diagonal matrix plus some low rank terms. And this is what the online LBFGS algorithm does. But you also have to consider there is a cost to that. If you approximate the Hessian with something that's basically rank k plus a diagonal term, you already did that one. The cost of each update will be k times more expensive because you're going to multiply the gradient by your rank k approximation. And that means that you need to go at least k times faster, otherwise it's not worth it. And that's one of the problems that people often meet when they do this kind of stochastic gradient descent, that they do less iterations, less epochs, but each of them is a lot slower. So it's not clear that this is a game. We did the SGDQN, which was a diagonal, because that's the only way we could achieve a gain. That was the going to the extreme. Or more exactly, the additional cost of applying a diagonal is really small. So any gain we can achieve that way is for our pocket. If you do just rank 5, the cost of each iteration is going to be 5 or 6 times more expensive. And you better go 5 times faster or 6 times faster, otherwise you gain nothing.
But depending on your data, you can go sometimes. You can always.
There are cases where this could be useful. I've been told about them. I never met them, but people told me that they had cases where this was useful. The averaging process, on the other hand, is very fast. It's no more than twice expensive. Typically, it's plus 20% because the cache is already primed with the right values. And so you can say it's 20% slower per iteration. So that can be really cool. OK, I'm sorry I finished early again. Thank you very much.